Okay. Our final speaker for today will be Fabricio Souza from Institute of Physics, Federal University of Rolandia. And the talk will be about quantum entanglement with semiconductor quantum dot devices.
Okay, so thank you again, the organizers, for this opportunity to share some of my recent research. So, I think it's yeah. Okay, so this is our collaboration team. Liliana from UFO, Ellen, she's here somewhere. Oh, Ellen is over there. PhD student, Elio and Kai also PhD students, and Midana Sambu, and also Dr. Sharmila from England. Okay, so this is the very beginning of this technology. This is the first transistor ever made from 1947 by Bardeen, Brenton, and Shockley at Bell's lab. It was made by germanium. Later on, they realized that silicon would be much better and more cheap to develop this kind of device. And the 1954, just a few years later, they developed the first transistor-based computer. So it's quite huge machine. And as time passes, the technology evolves and the number of transistors in a chip doubles almost every 2 years. This is basically the Moore's law that allows nowadays we have supercomputers like the one in the right side. And okay, this is the next technological breakthrough. We have a few companies nowadays that are developing quantum computers. Most of them are based on superconductor. We have Google, IBM, RIKEN, and the last one that was posted, I think, 2 weeks ago, contains 256 qubits. Okay, so it's quite a lot now. If you go to NASDAQ, you have already some companies there that are developing also quantum computers like D-Wave, IonQ, Riget Computing. D-Wave and Riget are also superconductor-based device, while IonQ is ion-trapped. If you look at the market cap of these companies, they are around $2 billion, which is quite small compared with big technologies like GPU and blockchain that is around $2 trillion. So we expect a perceivable increase of this kind of investments. Worldwide, we can see how it looks like. For instance, in the US, we have $7.7 billion being invested nowadays. Canada, around 2 billion. Brazil, it's we cannot read, but it's around $12 million, but it's actually more now. And China, it's quite impressive. We have something around $15 billion. Okay, so China is the main. We find the main investment on quantum computation in China nowadays. Okay, so, and these are some of the main platforms that the quantum computation will be developed. We have superconducting. Probably the first generation of quantum computation will be superconducting based because they are very advanced nowadays with 256 qubits, as I mentioned. But we have also quantum dots, color centers, trapped ions, topological protected systems. Okay, so we will focus on quantum dots device that can be also used. Okay, so here is a table where you can see some of the platforms and the qubit-based physics. We'll focus on this gate-defined quantum dots that can provide you a spin qubit and charge qubit. And there are also other ones. If you are interested in Majorana zero modes that can also be applied, you can attend the Poliana talk tomorrow, Wednesday, right? Okay, so quantum dots are very small devices that confine charge and spin in all the directions, okay, the three directions, and they can be quite well controlled using gate voltage like the ones here above. You can, I don't know if it is, no, I think it's not working. The laser, no. Okay, but anyway, you have some gates that you can put on top of two-dimensional electron guys, and you can generate localized states in a very well-controlled way. Okay, so you can adjust many of the parameters, like the coupling between one dot and the other dot, and also in a time-dependent way. Okay, so to model this kind of system, especially the fermionic, okay, thank you. Especially the fermionic devices like electrons and nanotransistors, we need some theoretical framework. We developed this kind of representation. It's fermion to qubit mapping of the system, which means basically that the entire universe becomes qubits. Okay, so everything turns into qubits, and we can write any annihilation operator, fermionic, I mean, in this way, with Pauli matrices, sigma z, sigma minus, and so on. Well, the main advantage of this framework is the computational basis that it's generated automatically, okay, in the Fock space. The system is divided in subspaces like A, B, C. Fermionic algebra is fulfilled, so we have the anti-commutation relations for fermions, which automatically provides you with the Pauli exclusive principle, Fermi-Dirac statistics. So this framework is something like a Lego framework where you have many subsystems that you can put them together to interact one with the other one in a very systematic way, okay? And you can also make closer quantum computation, the quantum transport theories via Lindblad formalism. Okay, so we allow charge to fluctuate in the system. So the system is basically open. We can inject the charge, we can remove charge from the quantum system. Okay, so let's say that we have subsystem A with 0 and 1 states. So this is basically a qubit. Subsystem B, which is also qubit. And you have something in the middle that we say it's C. And this kind of system can somehow couple A to B and generate some entanglement between these two states. Okay, something like here in the Lego, we have this piece A, this one B, and there are some additional subsystems that make the connection between them and allow them to interact and become entangled. Okay, so we have many body interactions like phonons, impurity, superconductor, photons, non-Markov environments. And what we make is basically a many-body quantum engineering. We play with many-body effects in order to generate entanglement between subsystems, okay? And this can be fermionic system, can be fermionic plus bosonic systems, like phononic microcavities, polariton, electron-phonon coupler, and so on and so forth. The to make our calculations, we use some packages like Qtip, Quantum Toolbox in Python, NumPy, Pandas, Matplotlib, and they are based on object-oriented programming language. Let me start describing one of our recent work. We have an array of 4 quantum dots. These two compose a qubit, and the two bottom, these two compose another qubit. And we have a charge qubit here, which means that depending on the position of the charge, we have 0 or 1, let's say. If the qubit, if the charge is here, we have 0. If it's there, we have 1. So we have a two-level system based on charge. I know that the phasing for charges is actually high with limited this kind of technology, but it would be nice to have quantum computers based on nanoelectronics, because we have the whole industry already set for nanoelectronics based on silicon. So it would be great, actually. And we are investigating and proposing some geometries and the interactions that can allow the formation of entanglement and the creation of some quantum gates like Hadamard, swap, and so on. Okay, so in this system, we have an interaction, a hopping term between these quantum dots, the Coulomb interaction between the populations in each quantum dot. Here we have time-controlled, you can inject in a time-controlled way electrons from the left lead into the dot and also from the right lead into another dot. And these injections can be actually performed experimentally, but it's tricky actually, because we want to create a state like this one, 0, 1, 1, 0, where 0 means 1 electron in the dot and 1 means no electron in the dot. So we need some configuration like that. But it's not a matter of open the system and inject charge to initialize, because if you open your system and keep it open for some time, you impose some dephasing to the system, so you cannot generate entanglement with that. On the other hand, if you apply a very short pulse to initialize, you don't achieve the target state, so you should find an optimized parameter to do that. And this plot shows the fidelity with respect to the initial target state that I mentioned, where here is the width of your pulse, and here's the tunneling rate. I mean the rate to inject the charge into the qubit, from the lead into the qubit. Okay, so depending on the parameter you choose, you can find a high fidelity with respect to this initial state. Curiously, when you compare it to the negativity is a way to quantify entanglement in your system. We find a very strong correlation between negativity and the initialization procedure. Okay, so if you tune sigma and gamma, the width and the strength of the pulse, we can enhance also the entanglement in your device. Okay. This is what we find here. If you look the fidelity, this is the target state now. It's a Bell state. Okay, a high entangled state here. And when we calculate how the fidelity evolves after the initialization, we notice that depending on the parameters of the width and the intensity of the pulse, we can have a high fidelity being achieved, like here in the black line, or a lower fidelity, like the dotted line, right? If you calculate the entropy of the system, you notice that after initialization, you keep some finite entropy into the system. So even if you, when you open your system and you initialize it, and after that you close it, you already damage your quantum dynamics. Okay, so you will not be able to create completely 100% fidelity in this system due to the initialization procedure, right? Also, we have the negativity. The negativity can quantify entanglement, as I mentioned. So we see also that in the optimized configuration of the gate pools, we have a relatively high fidelity for discharge qubits. High negativity for discharge qubits. Okay, and unfortunately, in real life, we have dephasing, and the dephasing for qubits based on charge is unfortunately high, around the nanoseconds. So when we introduce dephasing in our model, we start to see that the negativity is becoming suppressed, okay, which means that the system is evolving to a mixed state. Okay, so we start to destroy the entanglement of this device. Okay, but if you make your operations in the very beginning, you can still have fidelity close to 75%. It's low actually compared to a superconductor qubits, but anyway, this is electronic device. Okay, so if you improve it, it would be great. But we find we find it closer to 80%, something like that. If you manage to put it higher, it would be better, of course. Okay, so let's move on. This is also another system. It's based on superconductor. Actually, we have two quantum dots coupled to a superconductor in a geometry that we call Cooper pair beam splitter. We have a cross-down derivative reflection here that inject the spin up in one quantum dot and spin down in the other quantum dot. And here we find the interactions that we account for. We have Coulomb interaction, we have cross-down derivative reflection, and also Cott tunneling between these two quantum dots via the superconductor. We are also apply the mapping between second quantized operators and the qubits. What happens here is that we can generate very high entangled spins in this due to cross and derivative reflection. Here we plot many quantifiers, let's say. Curiously, we have covariance here between populations of spin up and spin down in the different quantum dots. Okay, and we have also concurrence. Concurrence is a quantum is a measurement for quantum entanglement. So it's curious that the covariance goes up together with the concurrence. Okay, so covariance is not a measurement of entanglement, of course, but somehow it can give you some insight, at least for the experimentalists. Okay, because in the experimental point of view, you not go in the lab and put your device and measure the concurrence. Okay, so you should measure covariance and the coincidence, things like that. Okay, so this is some. So covariance can give you some idea if it's entanglement or not. But if you introduce the phasing as well here, we notice that the covariance goes to 1 as time evolves, while the concurrence goes to 0. Which means that the concurrency tells you that it's entanglement or not. So we see that as time evolves, the concurrency goes to 0. So the entanglement is completely destroyed, okay? And while the covariance goes to 1. So possibly the covariances give you some insight on the entanglement degree if you are in the more closer to the pure state, you know, instead of the mixture that you reach in the end. Okay. Okay, let me talk a little bit about density matrix reconstruction. Okay, so we have a density matrix that gives you all the physical properties for your system. And if you want to quantify entanglement, for instance, you need to pass through the density matrix. So this is a fundamental operator to be determined from the experimental point of view. Okay. So suppose that we have a source that is spin polarized, let's say in the z direction, and this source starts to inject charge into a quantum dot. Okay, oh sorry, the Hamiltonian was here. And this other reservoir this lead is a drain lead that which you can rotate the magnetization of the system. Okay, you can put in z, x, or y direction to collect the electrons from the dot. A magnetic field is applied in order to rotate this spin in the quantum dot. Okay. What happens as time evolves is something like that. If you look the block sphere for the system, we start, let's say, with 0, which means spin up. As time evolves, this state goes to a mixture of states. And this dephasing is mainly due to the measurement. Okay, so when you start to measure your device, you start to destroy it as well, because there is no way you introduce dephasing when you are put some sort of detector on the qubits. Okay, so we try to simulate this detection procedure. You know that we can detect single charge tunneling processes in nanoscopic devices. We simulate that. And what we get in our detection simulation is the counting of number of tunneling events in different spin components. For instance, Z plus, Z minus, we have this kind of oscillations. The oscillations are going down due to the detector, of course. While in the X direction, we detect something like that, some exponential, decreasing exponential. And in the Y plus direction, we also observe some oscillations in the detection of the tunneling events of the electrons get out the dot, right? Okay, so we put all this data inside a modeling. Okay, artificial intelligence modeling. We come with the data, we put in the training, we train the machine with that data that we collected, build the model, and we get a predicted outcome. Okay, so this is all based on machine learning algorithms. And what the machine gives us is this kind of Stokes parameters. Okay, this is imported from the photonic field. Okay, we use also here in the spintronic field. And the computer find the model to fit all this data. Okay, and with these parameters, we can reconstruct the original density matrix of the system. So what you see here, this is, sorry for that, it's very simple. This is the density matrix. Let's say this A, B, B star C. We have some mathematical structure like that. And what we are seeing here is each one of the elements of this density matrix. A, you see here. C, you see here. And you can find the real and imaginary part of B, the off-diagonal element. This is the point. If you go to a lab and measure only the Z component of this charge transport, you, in the end of the day, you get this A and C, but this will not tell you basically if you are in an entangled state, if you are in a poor state, a mixture. You don't know. You actually need the off-diagonal element as well to build the entire density matrix. So we formulate a way to perform a quantum tomography. I mean, we reconstruct the density matrix of your cube based on spintronics. Some of these ideas we import from the photonic field and try to apply here. Okay. Also, we have this ongoing project. We have some semiconductor attached structure. By the way, Ellen will explore some more this device in her talk next week. Okay, so don't miss her talk. We have some semiconductor doped with manganese. We have some semiconductor here with quantum dots, and also Z and MNC on the other side. Okay, it was found experimentally that the interaction of spins in this quantum dot with the manganese induce some Zeeman splitting also in the quantum dots. Okay, so we use this idea to couple these two spins with the manganese with the doped manganese. This is the model that we use. And so we have four subsystems here in our Lego framework. We have two quantum dots, photo-excited, and we have two manganese and environment. So what we observed is that we indeed induce entanglement between these two spins, one in each quantum dot, mediated by the doped layer of the semiconductor. Okay, so and you get a very high fidelity. Okay, so we are basically applying here a Hadamard-like gate where you have some initial state that evolves to an entangled state here, right, mediated by manganese. And when we show the negativity, we did observe that it go very high, close to 1, meaning that you are obtaining very high quality for entanglement here. Also, if you go more to optoelectronics, here we have two quantum wells, okay, and we have some laser that pump here and those create the exton, and this exton interact with the photon and generate some exton polariton modes inside these quantum wells. And these polaritons can interacting with acoustic phonons that are driven by this technology here, based on this native communication. Only 5, okay. And when you model this with this kind of Hamiltonian, that's where we have some hopping between polaritons, between quantum wells, and coupling to acoustic phonons. And we notice that we can also drive high entangled polaritonic states. Okay, so we have polaritons in different quantum wells, and we are able to put the entangled due to the coupling with virtual phonons. The funny thing is that the phonons should be virtual, actually not real phonons, because if you start to create real phonons, you destroy the entanglement, okay, for the system. And finally, I'd like to show a little bit about this configuration composed by 3 quantum dots. Okay, we inject the charge in one of the quantum dot, so we have a double occupancy. How these two charges can jump into the third quantum dot, okay? They cannot pass straight for the second quantum dot, as we assume that the middle one is very small, so we have a huge Coulomb blockage that forbids these two particles to go from one side to the other side of the system. However, if they undergoes virtual transitions, the two spins in one side can end up in the other two side, mediated by 1, 2, 3, and 4 virtual process. And it's interesting that at the end we have this side behaves as a qubit as well, where we have two double occupancy being, let's say, 1, while vacuum 0. So we have in one side can be grounded and excited state, and the other side you can also have a grounded and excited state, where excited means double occupancy and the grounded means no occupancy at all. And when we calculate the entanglement for this Coulomb blockade based device, we observe a very high entanglement in a state like this one, right? This can be scaled to more and more sides. We can increase the size of this device. Okay, this is we observe it for large systems, and that's it. We develop this theoretical framework that allows to describe basically any sort of system. Of course, there is a problem of scalability because this computational basis in general goes exponentially, increases exponentially, right? We analyze quantum many-body engineering to generate high entangled states. And this is a proof of work that semiconductor nanoelectronics can be a potential candidate for future implementation of quantum computations. Thank you.
Okay, thank you. I think we have time for 1 or 2 questions. Yeah, there's one in the back.
Thanks, Fabricio. So I have a question regarding the first part. So if I understood you well, you're proposing an electrical way of initializing entangled states. And this is like purely due to how you like generate the current in your lead. So so the fidelity that you have there, it's with respect to, let's say, like pure Bell state. And I just wanted to understand whether the noise is playing a role in decreasing the fidelity of your system. So for instance, when we have like this lead with like current on, you're going to have the broadening of the quantum dot energy levels. So I'm just like wondering whether the deviation from 100% of fidelity comes from the noise from the lead, or just from the inability of really do something super similar to the Bell state.
Okay, yeah, good question. Actually, we have both of them. While the system is open to drive a current to initialize the system, we impose some sort of dephasing, right? But then we close it again, and we have the effects now of the background, the charge background that is fluctuating, and induces some dephasing as well. So the dephasing imposed by the leads is only the very beginning, when you are initializing the quantum dot. Okay. After that, it's the fluctuation of the gates voltages inside the device that induces the dephasing. Okay, so
you're assuming
you cannot separate the two in the end of the result. Okay.
Right. So you're saying that your dephasing is kind of step-like function once it's.
Yes. Some part of them, yes, that's true. is this one, yeah. Yeah, if you not see here, if you have 0.01 gigahertz for the phasing, which is very, very small, almost you don't have the phasing, you have a negativity. Also the fidelity, you will find it not at the 1 exactly. Okay, these you can say that is due to the leads that inject charge into the system. Okay, so if you, but and they do not decrease as time evolves. Basically, they continue relatively high. Okay, this is the best value that we found. Okay.
Yeah, awesome. Thank you.
Okay. There's one more question.
So in one of the earlier slides, you had some identity between DM, the fermion annihilation operator, with the sigma operator, right? I think it was like in the beginning when you did a fermion to spin mapping.
Yeah.
Yeah, that thing at the top. So D, is that a fermion annihilation operator?
Yeah, it's a fermionic operation.
That can be written as a tensor product of
spins. Pauli matrix operators, right.
I see. So how, is that an operator identity? Some sort of identity? It looks...
Yeah, it's a sort of Jordan-Wigner transformation.
Oh, okay.
For the
so it's kind of like reverse Jordan-Wigner transformation.
Yeah.
Oh, I see.
Something like that.
Okay, so so.
And with that, you can fulfill this fermionic algebra. Mm-hmm.
Okay, we're running out of time. I think we're a little over. So let's thank Fabricio again. And thank all the speakers for this afternoon's sessions.
Thank you, Bill, very much for kindly volunteering to chair this session. And thank you, Fabricio, for the nice talk. So tomorrow morning, we have a full morning of talks.